In this video, I want to talk about something called hybridization. And hybridization is really just this idea of explaining why certain covalent bonds can happen, because Lewis dot diagrams sort of fail to explain certain bonding. And so we rely on these two theories called valence bond theory and molecular orbital theory to explain that. So starting off with valence bond theory on the right here. It's basically this idea of orbitals come together and they just mix, and there's some rules that need to be observed. You can only have two electrons in that orbital, right? Like as we saw previously in our energy level diagrams. They must have an opposite spin, and overlapping is maximized. So let's look at an example of, let's say, H2, a diatomic element. If you recall, there's something called Hofbrinkel, and you can tell which one, which elements naturally occur as a pair. So the way valence bond theory would explain this is that, well, if we had a hydrogen here plus another hydrogen here, so these little dots with circles are hydrogen, and this is a 1s orbital, and this is a 1s orbital, right? And if we add these two together, if these two orbitals just mix together, and then the mixing further increases, then you get this weird looking donut shape, and the dots represent the nucleus, and this is what you get, 1s2. And that's like the visual representation of valence bond theory. So this explains why, sort of there's a lot of stuff behind the scenes to explain it, but visually valence bond theory is just this idea of orbitals coming together and completely overlapping to form the certain orbital. Now this theory has its limitations. It can explain for some things that are going on for some sort of stuff. So we use molecular orbital theory a lot, and we're going to use it mainly more than valence bond theory in this course. And so molecular orbital theory is just that covalent bond formation happens because of delocalized electrons. So atoms will, when they're about to form a bond, they'll delocalize their electrons in a way to make sure the bond happens. Because in their natural state, when they're unhybridized, because the word hybridization means to just mix it up, form a hybrid of two things. When they're unhybridized, they can't really bond. They can't really connect with each other. So molecular orbital theory just explains that as to like why these elements do this so that they can bond. So there are two kinds of bonds you need to know. These are two bonds. The first one is called sigma bond, and it has this weird symbol that looks like this. Sigma bonds are end-to-end overlap of orbitals, and this can be either s, p, or hybrid orbitals. They're symmetrical and they can freely rotate. So an example of a sigma bond would be, let's say, of just a 1s orbital just overlapping with another 1s orbital. Sort of like what we saw here, except they don't fully, mix together and make that shape. They're just, they're overlapping sigma bonds. And so, this could be a 1s, this could be a 1s, and there'd be electrons in between. That's a sigma bond, and it's represented by this weird, almost looking 6 symbol. Like, oh yikes. Like this, sort of. The next one we have are pi bonds. Pi bonds are side-by-side parallel overlap of p orbitals. So it looks like, so this is a p orbital, and basically a side-by-side overlap will look something like this. So there's another p orbital. This side-by-side overlap here, that's what makes it a pi bond. Just these side-by-side overlaps. So sigma bonds are end-to-end overlaps, and pi bonds are side-by-side. And pi bonds are responsible for double and triple bonds. And you'll see that in a second why. So that's basically it. There are two kinds of bonds, and we're going to see now how electrons sort of delocalize themselves so that they can bond. So let's look at an example of methane. If we draw the Lewis structure diagram of methane, I'll do the hydrogens in pink. Right, this is what it looks like. So you know that, well, okay, carbon makes 4 bonds, because it even has like that 4 charge. But let's look at its electron configuration. So its electron configuration is 1s2, 2s2, 2p, 2, right? If we draw the energy level diagram, we'll notice something a little interesting. So, looking at this energy level diagram, carbon can only form 2 bonds. It can form a bond here and here. It cannot form a bond here because it doesn't have an existing electron for hydrogen to just come in and put in. There is no electron that exists for hydrogen to happen. For hydrogen to, share its other electron, right? There's nothing going on over there. So, how is carbon making 4 bonds? Well, this is where we do some electron delocalization. So I'm just going to draw a little down arrow here and redraw this energy level diagram. In our 1s, we have 1 electron, 2 electron, right? But now here's where we do some, some interesting stuff. If we wanted carbon to have 4 spots so they can form 4 bonds like it is in methane, we would have to promote an electron. And in this case, we're going to promote this electron here in the s orbital and stick it right up here. So it would look like this. Now carbon can make 4 bonds, right? Because hydrogen can come here, hydrogen can come here, hydrogen can come here, and hydrogen can come here. This is called hybridization, the idea of mixing orbitals. We just mixed an s orbital with a p orbital. And so really what the diagram will look like for this hybrid orbital would be, well, you have your 2s here, and then you have your 2p here. They're actually the same energy because hybrid orbitals, when you mix them all, they just become the same energy. So same E, right? And then we just put our electrons in like this. This promoted electron. And then hydrogen comes in like this and fills it, right? Now, we need to give a name for this hybridization so we can classify it. How do we name it? Well, we're going to name it accordingly to how many mixed and how many are making like the single bond. So we used 1 s orbital and mixed it with 3 p orbitals, right? So this would make it S, because 1s, P, 3 hybridized. Carbon has now been sp3 hybridized. This is the classification we would give it. That's just the way we communicate it. So the exponent on the letter will tell you how many of those p orbitals are being used to make sigma bonds. Keep that distinction in mind, to make sigma bonds, right? This symbol. Because this is a sigma bond, this is a sigma bond, this is a sigma bond, this is a sigma bond. So that's methane, and it's this idea of promoting electrons. Let's look at another example. Let's say we did C2H4, aka ethene. I'll make my hydrogens in pink. Oh, that's not pink. Hydrogens in pink. All right. Let's restate the electron configuration again. Carbon. Let's look at, this is a different situation now. So we know this is going on, right? Now, we have a double bond here, so we know we're dealing with a pi bond. But we are not going to just promote this guy up here and then call it sp3. It's not going to be called sp3. Our hybridization is a classification of the single bonds only. So what does that mean? So if I drew this again, one s like this, bang, 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 and right here we see that there's 4 spots, right? But only 3 of these are actually going to be used. Only 3 of these are going to be used. So how does that work? Maybe I should do this in a yellow. So only 3 of these, okay, green. Only 3 of these will be used. And one of them will be used for the pi bond. So this one over here will be used for the double bond, the pi bond, while these will be used for the sigma bond. And you may be wondering, how the hell does that make sense? Let's look at this Lewis structure right here. We have a hydrogen here, and we have because we're looking at this carbon here. The carbon is bonded to one hydrogen and another hydrogen. So let's just write that on this thing. Okay, let's just say it's bonded, hydrogen's bonded to this, it'll dump its electron here. Hydrogen's bonded to this orbital, so it'll dump its electron here. What about this other one? What's going on here? Well, carbon is still bonded to another carbon, right? And a double bond does not, like, this whole thing is not a pi bond. A pi bond is just when you add another bond to make it a double bond, if that makes sense. So one of the bonds going on here is a sigma bond, and the other bond you have going on here is a pi bond. So this guy is responsible for the sigma, and if you add another, it becomes a pi bond. So, in other words, actually I'll leave that here. You're adding a carbon here, carbon, and then carbon would put its electron here. So hopefully that made sense, but that's what we're doing. So if we're only using 3, then we would call this, because this is 1s orbital, so it's 1s orbital plus 2p orbitals. So I should write like this, 1s orbital plus 2p orbitals. Well, the hybridization classification would be sp2 hybridized. That is the hybridization for carbon. Because again, we're using 1s, or we're using not 1s. We're using one singular s orbital and 2 p orbitals to achieve these sigma bonds. And the remaining thing we have is this remaining orbital we have is for the pi bond. And so if we redrew that thing I drew last time in terms of the energy level, it would look like this. So we have this, right? This would be sp2, and this would be 2p, and this is where that other electron would be chilling. So this would form that pi bond. So I'll draw a little visual representation of how that looks like. So we have a carbon here, and we have it bonded with this other carbon, so it's sharing these electrons. There's another carbon here, right? We have this bonding going on here, this overlap of orbitals, right? These are the hydrogens, or actually I should do that in pink to make it clear. We have this overlap, right, going on here. Hydrogen, hydrogen, bang, bang, right? Then we have, this going on here. Clear, that's a dot. 1 dot, 2 dot, and then hydrogen, right? Because it's C2H4. Right? It's C2H4. I'm just drawing the same thing, zooming out. I'm just drawing the same thing, but over here, a visual representation of what's going on. Right? So if we had to label the sigma bonds, this would be a sigma bond because it's just a single bond, sigma bond. Here we have a sigma bond going between the carbons, sigma bond, right? Now we draw in the p orbitals. P orbitals look like this, the little dumbbells. And so you may be wondering, okay, how the hell are these two overlapping? Well, there is a little interaction going on here. I'm not the best artist, but this would be a pi bond. And another way to imagine this diagram I just drew is to look at it like this. So let's say the shaded in represented carbon. All right. had this little, looks like a little burger. I assure you it's not though. And this is the hydrogens in pink. That's what it looks like. And this top up here is the p like the pi bonds. So this p orbital here and this p orbital here are interacting, and they sort of form like this sandwich on top. So they are like overlapping. So hopefully that made sense. I know this is incredibly confusing visually speaking, but that's really what's going on. If you can sort of get this image sort of, you know, in your head of how it sort of looks like, then it makes, you know, somewhat sense. But it's this idea of we classify hybridization according to the single bonds. Let's look at one more example. Last one. It's almost over. Ethene. Ethene. Or C2H2. This will look like this. Triple bond here, hydrogen here, hydrogen here. Again, the electron configuration of carbon, 1s2, 2s2, 2p2. It'd be 2p up here, 2s up here, 1s. Alright, just drawing it. Alright, we have another situation. So again, we classify the hybridization according to the single bonds or the sigma bonds. So we have a triple bond going on here. When we see a triple bond, the idea I need to have in your mind is that, okay, that's one sigma bond. Oh, that just looks like a 6. This is a 6. One sigma bond plus 2 pi bonds gives us a triple bond. That's what's going on here. So we're going to do that same step again. Swing this guy over here. 2p, 2s, 1s. Right? But this is not sp2 hybridized or sp3 hybridized. This is sp hybridized. Let me do it in the white. This is sp hybridized. And you may be wondering, how does that make sense? Oh, I forgot to make my hydrogens pink. So one carbon, looking at just one singular carbon, is bonded to an hydrogen. So hydrogen will dump its electron here, and we can circle this carbon in this red, and it's bonded to another carbon over here. So it shares its electron here, right? And the remaining 2 bonds in between here, those are just the 2 pi bonds. That's it. So what we're left with, so here, these are the 2 pi bonds. So since only one s orbital, looking at these two, since only one s orbital, no, I keep writing it like that. Since an s plus a p orbital, right, we're just going to call this sp hybridized. Because only an s and a p orbital are really mixing to achieve the single bond we want. And then these two, we would call these, you know, unhybridized. Whenever you have pi bonds, you call that unhybridized because you're not really dealing with that. So if I drew like a visual diagram of this, it would look like this, right? sp. So this is sp here, right? And then I have that electron here, and then I have this electron here, and then this, and then this. So sp, and this is 2p. This is the pi bond stuff, and this is the sigma bond stuff. We always hybridize. The hybridization classification we give is according to the sigma bonds. So let's say I drew a visual image of this, because I'm sure the last one was incredibly helpful. It totally made intuitive sense, I bet. But again, it's like this. The 2 electrons are being shared. And I'll color this carbon in red. Right, we have this going on, because this is the hydrogen. We have this going on. the hydrogen, right? Let me just write sigma bond up here. Yeah. Right. And now in that first example, I drew only one p orbital on both sides, and that's to represent you know, double bond. But if you have a triple bond, we draw two p orbitals. Yikes, that second one was awful. So the way to think about it is that one of these would be like, you know, py, the other one would be like pz, right? Because remember, if you recall from the quantum numbers video, this would be px, py, pz. These are just different orientations. So the pz's would be interacting with the pz, the py would be interacting with the py. So there's some interaction going on between here. That's one pi bond, you know, that same level of interaction going up top. They're you know, side to side overlapping. And then this py is interacting with this guy over here. That's a pi bond. And then this guy's interacting over here. So yeah, I'm sure this, visually, this looks amazing. But that's really it. So I can just write this at the bottom, SP hybridized. So those were the three examples I wanted to go with today. The next video, we'll go through 3 more examples. It'll explain why we can have incomplete octets and expanded octets. That'll probably make a little bit more sense than this stuff, hopefully. But if there's one main takeaway you need to have, is that sigma bonds, single bonds, pi bonds are double and triple. And hybridization is all about moving electrons so that we can make the bonds happen. Yeah, and let me know in the comments if this video was helpful, if there's something I could explain better. I always look for feedback, you know, to improve the videos, because at the end of the day, I create these videos to help you guys, so I hope I'm achieving that goal. But yeah, this is part 1 of the hybridization stuff, and you know, the fun is only beginning. So see you in the next video.